this video we are to prove that integral from 0 to 1 of y raised power of n ln of y raised power of x dy is equal to minus 1 raised power of x divided by n plus 1 raised power of x plus 1 gamma of x plus 1. So we have to prove this. So for we to prove this, first of all, let's let I to be equal to integral from 0 to 1 of y raised power of n into ln of y raised power of x dy. That is the left hand side. Let I to be equal to the left hand side, and then we are going to also let ln y to be equal to minus t. Let ln y to be equal to minus t. So if ln y is equal to minus t, I will take exponent of both sides to eliminate this ln. We're going to have y to be equal to exponential minus t. Take exponent of both sides, we have y to be equal to exponential minus t, and let's call this equation 1. Let's call this equation 2. So differentiating equation 2 with respect to t, differentiating dy with respect to t, we are going to have minus exponential minus t dt, and let's call this equation 3. So we've gotten 3 equations already. Now substituting back equation 3 and 2 into equation 1, we are going to have I to be equal to integral from 0 to 1 of y raised power of m. Now instead of having y raised power of n, we already have y to be equal to exponential minus t. So we're going to have exponential minus t raised power of m. So that is mt, exponential minus mt. Then multiplying ln y, we have ln y to be equal to minus t already. So we have minus t here. We have minus t. Then this raised power of x. Then dy. Dy now is minus e raised power of minus t dt. And let's call this equation 4. This equation 4. So we are going to be solving equation 4. We are going to be solving equation 4. So let's rearrange this. Now we are going to change this limit from 0 to infinity from here. We are going to change the limit from 0 to infinity because we are dealing with it in a polar form. We are dealing with it in this form rather. So we are dealing with it in this form. So it's going to be from 0 to infinity. Of course, if we also substitute the value of 0 and 1, substitute the value of 0 and 1, we're going to have so this is what we have. So now we are going to be solving this. Check, these are the same basis almost, except for this minus. So we are going to be solving this, we are going to be multiplying these two. So of course we have minus here, so let's bring the minus outside. We have minus t raised power of x, and this multiplying this, we are going to have exponential mt. Exponential mt, we have minus exponential mt plus t here, minus exponential mt plus t dt. So that's what we have there. Then let's take this further and let's change the int. Integral from 0 to infinity, we are going to have this to be, now you can split this into 2. You can split it as minus 1 raised power of x, and you can split it as t raised power of x exponential minus n plus 1 multiplying t dt. So this is actually the same thing as this. If you multiply this now, minus 1 and t here now, we are going to get the same thing. So it's the same thing with what we have above there. So now what we are going to do next is we are going to let m plus 1 t, that is this power here, we're going to let that power to be equal to u. We're going to let this power to be equal to u. So that means t is going to be equal to u divided by n plus 1. And if we substitute, if we differentiate t now with respect to u, we're going to have the u divided by n plus 1, the u divided by n plus 1. That's what we have. If we differentiate um, t with respect to u, we have this. So we are going to substitute this in this equation again. We're going to substitute, let me call this equation 5. We're going to substitute all of this in equation 5. Then that means I is going to be equal to integral from 0 to infinity of minus 1 raised to the power of x. And instead of having t, we're going to have u all over n plus 1 all raised to the power of x. Now you have exponential. Instead of having minus 1 minus n plus 1, and we really substitute to the u, so we are going to have minus u instead. And then instead of having the t, we are going to have the u divided by n plus 1. So I now is going to be equal to integral from 0 to infinity of minus 1 raised to the power of x multiply u raised to the power of x divided by n plus 1 raised to the power of x multiplying the exponential minus u multiplying the u raised to the power of n plus 1. So I is going to be equal to integral from 0 to infinity of minus 1 raised to the power of x. So you can actually add this base here since they are the same. Divided by, we're going to have n plus 1 raised to the power of x plus 1 exponential minus u du. So I is going to be equal to, and you can bring it outside. Bring it outside, we are going to have it to be. Let's bring this minus 1 outside and divide it by n plus 1 all raised to the power of x plus 1 integral from 0 to infinity of u 0 to infinity of u raised to the power of x. Then you are left minus u du. So at this point now, I is going to be equal to minus 1 raised to the power of x divided by n plus 1 raised to the power of x plus 1 integral from 0 to infinity. Now let's look critically at this. Let's look very critically at this. So you can actually have this be u raised to the power of x plus 1 minus 1, of which x plus 1 minus 1 will still give you x. So you now have exponential minus u du. So if you observe this now, you discover that this is actually equal to minus 1 raised to the power of x divided by m plus 1 raised to the power of x plus 1 gamma x plus 1, where gamma x plus 1 is equal to integral from 0 to infinity of u raised to the power of x plus 1 minus 1 exponential minus u du. So this is our proof here. This is the proof for this question. Please like this video, share it with your friends. Don't also forget to subscribe to this YouTube channel and turn on the notification so you could be notified each time we upload a video. Thank you.